Hello everyone, Dr. Hasbullah here, and in this video, we are going to be looking at momentum equation. We have learned before that conservation of momentum says that the summation of force is equal to the rate of change of the momentum inside a system, and it looks something like this. Summation of force is equal to d over dt, and this is rho v dv. And this is the integration of a system. And using the Reynolds transport theorem to convert from system to control volume, we found out that the summation of force is equal to d over dt, and this is the integration over a control volume, rho v dv, plus the integration of the control surface, rho times v velocity dot normal times dA. And as usual, what we do with this long equation is to simplify it using the assumption of steady and uniform flow. I'm going to write it here. So steady plus uniform flow. We know that when the flow is steady, there is no change in time inside the control volume. So this term will immediately become 0 because d over dt is 0. So basically, we are left with just this equation. So if I write it again, summation of force is now equal to integration of the control surface, rho v, v dot n dA. And when we assume that the flow is uniform, we can simply change the integration symbol to be just the summation of rho I times velocity I times velocity I dot n times AI. And I is from 1 to n. And I here is simply the number of entrance and exit. For example, if you have one entrance and one exit, this equation becomes summation of force rho 2 A2 V2 V2 minus rho 1 A1 V1 V1. And I think by now, because you have done conservation of mass and conservation of energy, you should know why we have the negative sign over here. And back to the assumption that this flow is steady, this means that m dot 1 is equal to m dot 2, isn't it? This means that rho 1 V1 A1 is equal to rho 2 V2 A2. Therefore, we can simplify this equation even further by writing summation of force is equal to m dot times V2 minus V1. Okay, so I think this equation is simplified enough. But we also know that velocity has direction, isn't it? It has x direction, it has y direction, and it also has z direction. So if we are to represent this velocity in terms of its own x, y, and z component, the equation becomes summation of force in x direction is equal to m dot v2x minus v1x. Okay, and this goes for y and z as well. So this is summation of forces in y direction equal to m dot v2y minus v1y. And similarly, in z direction, this becomes summation of force in x direction is equal to m dot v2z minus v1z. And the reason why we represent this into three components because the momentum equation is usually used to represent forces inside the pipe. For example, if you have a flow that goes from here and then it goes through the bend and it goes up. So naturally, if this is a pipe flow, then you know that this pipe is going to experience some forces from the flow, isn't it? The flow is going to force the pipe in this direction. So the way to find that force is by using this momentum equation. Now let's see how this equation works. First of all, if you have a flow inside a pipe, okay, let's say that the pipe looks something like this. And this is the wall of the pipe. And this pipe has a flange which is connected to another pipe by these bolts, and the flow goes in this direction. So what are the forces that is involved in this pipe? Let's say I'm going to take the whole pipe as my control volume. After this, we're going to see what happens if we just take the fluid inside the pipe as the control volume. It's going to be a bit different, but the answer should be the same. So for this one, I'm going to take the whole pipe as my control volume. Okay, so that is the control surface. And when you have the flow that goes in this direction, you can expect that this pipe will experience some forces. And this force will be held by this flange, isn't it? Okay, so I'm going to call this Fx joint. And this is my Fy joint. And another force that you are going to have when you have a flow that goes into the control volume and exit of the control volume is what we call the pressure force. And the force that comes from the pressure is simply pressure times area. So at point 1, you are going to have, let's say this is point 1 and this is point 2. So at point 1, you're going to have P1A1, and at point 2, you're going to have P2A2. And if you notice something here is that the direction of the pressure at point 2 is actually directed inward. So the pressure force is directed into the control volume. This may sound a little bit strange in the beginning, but later when you've done a few examples, you will see that this is the correct approach to solve for the pressure forces. So this is what my forces looks like when I include the pipe inside the control volume. What happens if we just include the flow inside the control volume? Let me draw this side by side so we can do the direct comparison. Remember that this is fluid only. We are not including the pipe itself into the control volume. So this would be my control volume. And first, let's mark our pressure forces. So this is P1A1 and this is P2A2. And when you have P1A1 and P2A2, you know that this fluid is going to have to be supported, otherwise it will move away. So I'm going to mark here and I'm going to call this F nozzle. And if we say that this flow is exiting the pipe at point 2, so we know that the flow goes from inside the pipe into the atmosphere. So we know that the pressure at point 2 is 0. So we can quite easily cancel this out. Okay, so taking this example, if I'm going to write the equation and I'm going to look for the force in x direction. So I'm going to be using this equation. Fx equal to m dot v2x minus v1x. So let's see what happens here. And in my x direction, what I have, summation of force in x direction. First, I have P1A1. Let's do positive to the right. So P1A1 is positive. And what else I have? I have here minus this force, right? This is Fx joint. And it seems like these are all the forces that's involved. And this force is equal to this term, m dot v2x minus v1x. So, let me write it here. This is equal to m dot v2x minus v1x. Now, let's see what is our v2x and what is our v1x. And looking back at this figure, let me write this again. So, P1A1 minus Fx joint equal to m dot. What is our v2x? Remember that at point 2, which is here, okay, at point 2, there is no velocity in x direction. Because at point 2, the flow is going up into the atmosphere. So, you only have Vy. You don't have V2x. So, this is quite simply 0. And what is our V1x? So, V1x is in that direction. 1 is inlet and 2 is exit. So, V1x is actually V1. Because at point 1, we only have velocity in x direction. So, this is minus V1. So this equation becomes minus m dot v1. And that is how you build the equation around the engineering problems using the momentum equation. And of course, you need to remember our original assumption that this equation comes from the assumption that the flow is steady and uniform. Now, let's take a look at an example. So if I have a pipe bend that looks something like this, and it has a different inlet and exit area, and this pipe bend is supported by two rods here and also here. Okay, and the flow comes from this side and exit into the atmosphere at the other side. And the information that's given to us is that this is a 37.5 millimeter diameter exit, and at inlet you have a 75 millimeter diameter pipe, and the flow rate of the fluid that is inside this pipe is Q equal to 8.3 times 10 to the power of minus 3 meter cube per second. And what the question is asking you is to calculate the force that is acting on the rods, on the supporting rods. Okay. So the first thing that I'm going to do is to draw the control volume of this problem. So control volume looks almost similar. And my control volume will be in orange. Okay, so this is my control volume. And what I have here is the forces of the rod. So this is Rx. And let's call this Ry. And remember, we also have pressure forces. So this is P1A1 at the inlet, and this is P2A2 at the exit. But since the problem says that this flow exits into the atmosphere, it means that P2 is equal to 0. So I'm going to completely remove this. But instead, I'm going to put here velocity at inlet, and this is velocity at outlet. So now I think that we have labeled everything. So summation of forces in x direction, let's do positive to the right. This is equal to P1A1 minus Rx, isn't it? These are all the forces that is acting on our control volume. And this is equal to this equation again. Okay, this is V2x minus V1x. This is equal to m dot V2x minus V1x. Except this time, we don't have V2x because at exit, what you have is V2, and V2 is in y direction. Okay, so this is going to be minus m dot times V1 because at point 1, velocity at point 1 is only in x direction. So V1x is equal to V1. Now that we have our equation for force in x direction, let's do summation of force in y direction. So let's do positive is upward. So this is equal to, what we only have here is Ry. So this is positive Ry and equal to m dot V2y minus V1y. Now this is equal to V2y is simply V2, right? And we don't have V1y, isn't it? Because at point 1, there's only V in x direction. So this is going to be m dot V2. And remember, what we are looking for is the Rx and Ry. So let's see if we have what we need here. So what we have is actually the flow rate. And when you have flow rate and also you have area, effectively, this is diameter, but you can easily convert it into area. And you know that we can obtain velocity at 1 and velocity at 2 because Q is simply velocity times area. So Q is equal to V1A1 is equal to V2A2. Let's deal with inlet first. This is V1A1. So Q is 8.3 times 10 to the power of minus 3 equal to V1. A1 is pi. What is our radius? this is our diameter 75 millimeter. So 0.075 square over 4, and that will give us V1, and V1 is equal to 8.3 times 10 to the power minus 3 times 4 divided by pi, divide by 0.075 square. This is 1.88 meter per second. And what about our V2? 8.3 times 10 to the power minus 3 equal to V2A2. So this is pi. Diameter at point 2 is 37.5. This is 0.0375 square over 4. So our V2 is equal to 8.3 times 10 to the power of minus 3 times 4 divided by pi divided by 0.0375 square. This is 7.51 meter per second. Right, now that we have V1 and V2, do we need anything else? Okay, so m dot is equal to rho VA. I think we have rho, that is water, 1000 kg per meter cube. Velocity times area is actually the volume flow rate, which we have here. And V1 we also have. So m dot we also have. But now we need P1. Okay, we know A1. And effectively we can already solve Ry, because for Ry we already have m dot and we just found V2. But now to solve for Rx we also need P1. And as usual, when we have velocity and we need to find pressure, we can go back to Bernoulli equation. And Bernoulli equation says, this is Bernoulli equation, that is V1 square over 2g plus P1 over rho g equal to V2 square over 2g plus P2 over rho g. And remember that our P2 is actually 0 because the water goes into the atmosphere. Right? So this is 0. And remember that we need P1. So P1 is equal to V2 square minus V1 square over 2g and everything multiply with rho g. And you can cancel g out, and we know that our V2 is 7.51 square minus V1 is 1.88 over 2 times rho. Rho is 1000. So our P1 is equal to 7.51 square minus 1.88 square divided by 2 times 1000. And you have here 26433 Pascal, or simply 26.4 kilopascal. Now that we have pressure, I do think that we have everything we need in order to find Rx and Ry. So let's do Rx first. So in here, Rx is equal to P1A1 plus m dot V1. So if I copy this equation and put it here, so our P1 here is 26433 times A1 is pi times diameter at point 1 is 75 millimeter. This is 0.075 square over 4 plus m dot is just rho times q. This is our rho and this is our q. Q is 8.3 times 10 to the power of minus 3 times V1, and V1 is 1.88. Let's see what is our Rx. 26433 times pi times 0.075 square divided by 4 plus 1000 times 1.88 times 8.3 times 10 to the power of minus 3. And this is equal to 132.4 Newton. Okay, and that is your Rx, meaning that that is your force for this rod, Rx or this one. Okay, and to find Ry is simply m dot v2. Let's write it again here. Ry is m dot v2. This is, so m dot is rho times q times v2. So 1000 times 8.3 times 10 to the power of minus 3 times v2 is 7.51. So this is 7.51, and this is equal to 1000 times 7.51 times 8.3 times 10 to the power of minus 3. This is equal to 62.3 Newton. And that would be your Ry, or the force on this rod. Okay, so this is basically how you solve an engineering problem using the momentum equation. So repeat this problem again and again and make sure you understand how do we get the momentum equation from the conservation of momentum. That is all from me for now, and I'll talk to you in the next video. Bye!